Hello, my name is Nicole Martin, and my capstone presentation is on the bioaccessibility of lead on the hillsides of the Bunker Hill Superfund site in Smelterville, Idaho. In this presentation, I will talk about the robust mining history in North Idaho, focusing on Smelterville and the Bunker Hill mining complex, how the area became contaminated with heavy metal, primarily lead, how lead is harmful to humans, my research into the current lead soil levels and how much of that lead is bioaccessible, the results of that research, and how far the area has progressed over the past 40 years. Smelterville, Idaho is in the heart of the Silver Valley, which got its name by producing almost 1 billion ounces of silver between 1884 and 1979. This area is also known for having rich ore deposits of lead and zinc, which allowed the area mines to supply an on-site smelter. By the time the smelter closed in the early 80s, it was producing 20% of the nation's lead and zinc and 25% of the nation's silver. The Bunker Hill Mine and Smelting Complex started in the 1880s with the opening of the Bunker Hill Mine. In 1917, the Bunker Hill smelter became operational and started smelting silver and lead. Over the following decades, additional heavy metal processes were added, as well as the production of sulfuric acid. In 1973, there was a fire in the main filtration system, and the following year, federal, state, and local health departments started investigations into the elevated blood lead levels of the population of the Silver Valley. The complex was closed in 1981, and the area was declared a Superfund site a couple years later. A baghouse fire occurred on September 3, 1973, and damaged part of the primary dust filtration system. Lead particulates released into the atmosphere increased from about 10 to 20 tons per month prior to the fire to 73 tons per month afterward. This led to a total of about 720 tons of lead being released into the local environment between 1973 and the summer of 1974. This figure shows the air lead concentration measured at 4 monitoring stations in the area within 4 miles of the smelter. In 1971, the air lead concentration was 7 micrograms per cubic meter, which increased to 30 micrograms per cubic meter in 1974 after the fire. The Clean Air Act set a limit of 1.5 micrograms per cubic meter of air lead concentration, which has since been lowered to 0.15 micrograms per cubic meter. Lead particulates in the air are not the only form of waste from mining and smelting. Mining produces a significant amount of tailings, which are leftover rock and ore after the desired metal has been removed and can still contain high levels of heavy metals. This diagram shows the breakdown of 1 ton of mined material. Tailings make up over 90% of the material. Zinc smelting produces sulfuric dioxide, which is either blown out the smokestack or harvested and turned into sulfuric acid. These, along with lead dust particulates, severely impact both environmental and human health. Due to the environmental impacts of mining, this area was declared a Superfund site in 1983, which allowed the EPA to come in and control the process by forcing the responsible parties to participate in the cleanup or reimburse the government for their efforts. The box is the nickname for the original 1983 Superfund site area and included the 21 square miles immediately around the smelter. Within this area, about 7,000 properties have had soil remediated by removing the top 12 inches of soil and replaced with clean material if the original soil had lead levels that exceeded 1,000 parts per million of lead or arsenic levels of over 100 parts per million. The Bunker Hill Superfund site has been expanded twice and now encompasses 1,500 square miles and includes 166 miles of river. Lead in the human body can damage the brain, nervous system, kidneys, as well as other systems in the body. In children, it affects the brain by causing behavioral problems, lower IQs, as well as learning disabilities that can continue into adulthood. In order to determine how much lead in the soil can make its way into human tissue, bioaccessibility is measured. Bioaccessibility is an in vitro measurement of the physiological solubility of a metal that may be available for the absorption into the human body. Bioavailable lead compounds include lead acetate, lead oxide, lead carbonate, and lead phosphate. In order to inform the population of the Silver Valley about the hazards of lead in the soil, the DEQ has published an activity book that is available on their website. This is one of my favorite pages, and it talks about cleaning items that may have contaminated soil on them before bringing them home. I chose the Bunker Hill Superfund site as my research location because it holds a special place in my heart. I grew up about an hour west of this location, and my grandfather actually worked at the Bunker Hill smelter before it was closed. My research goals were to sample soil from previously tested sites on the hillsides around the Bunker Hill Superfund site and determine the viability of using a laser-induced breakdown spectroscopy unit, or LIBS, for testing heavy metal contamination in soil out in the field. I would do this by confirming the LIBS results with ICP-MS analysis in the lab. This would provide information on how the heavy metal concentrations in the soil have changed over the past 25 to 30 years. Unfortunately, the COVID-19 shutdown of the university prevented me from completing my ICP-MS analysis. I was, however, able to complete a bioaccessibility analysis of these soil samples. This satellite map of the soil samples, this is a satellite map of the samples from the 1995 to 1998. These locations were selected mostly because they have a high probability of being developed at a future date. The locations I sampled are inside the pink box. It's really hard to tell in the legend, but the largest listed concentration on the map is 10,000 parts per million. This is a closer view of the pink box. This is a zoomed in picture from the previous slide. My locations are labeled, and I selected these locations because they are located on DEQ land and had a high lead level concentration back in the 90s. I used an EPA soil sampling method and took both up and downhill samples at depths from 0 to 1 inch and 1 to 6 inches using a hollow soil probe. At each location, I took 12 samples for a total of 36 samples for my research. And each of these locations were about 100 meters apart, and it gave a good spread of the area. So what is LIBS? LIBS stands for Laser-Induced Breakdown Spectroscopy and is a type of instrumental analysis. A LIBS unit uses a laser to excite electrons to a higher energy state, and as they come back to their ground state, they emit element-specific wavelengths of light. The detector array converts these wavelengths of light into a spectrum that is then compared to a library of spectra to provide the chemical breakdown of what's present in the sample. The level of detection for LIBS is generally between 5 and 15 parts per million, depending on the element. However, for lead, it is actually 1 part per million per the manufacturer. The LIBS unit is also able to provide a quantitative analysis of the elements present, provides an uncertainty using 1 standard deviation. ICP-MS, or inductively coupled plasma spectrum mass spectrometer, is a staple in all analytical labs. It works by aerosolizing a liquid sample using a pneumatic nebulizer in this diagram, passing it through argon plasma to ionize the atoms, and then moves the atoms to a mass spectrometer which measures the mass of the ions and provides a spectrum. This spectrum is compared to a library as well, and a chemical composition is reported. The ICP-MS is a lot more sensitive than a handheld LIBS unit and has a limit of detection of between 3 to 8 parts per trillion, with level detection for lead being about 6 parts per trillion. Since LIBS sampling works best, sampling a hard, flat surface, I created soil pellets by grinding my soil samples into a fine, uniform size and pressing them using a hydraulic press. The pellets were then placed on a piece of tape and attached to the window of the LIBS unit. I sampled 7 different locations with 12 spots per location on each pellet, as seen in this picture, in order to get an average concentration of the soil sample. The average value was then used to design individual dilution schemes for each soil sample, since both my bioaccessibility and ICP-MS analysis were concentration sensitive. The bioaccessibility experiment was based off the EPA method 1340, which is titled In Vitro Bioaccessibility Assay for Leaded Soil, which basically simulates the stomach environment. This is done by making an extraction fluid comprised of glycine dissolved in nanopure water and adjusting the pH to 1.5 at 37 degrees Celsius using concentrated hydrochloric acid. This extraction fluid, along with a soil sample weighing between 0.1 and 0.5 grams, were added to the flask and mixed for 1 hour at 37 degrees Celsius. The mass of soil used was based off the LIBS values, since this method is not designed to handle soil samples with a lead concentration of over 50,000 ppm. After an hour, the mixture was removed from the shaker box and allowed to settle for a few minutes so that 10 milliliters of supernatant could be extracted. This extract was then filtered through a 0.45 micron filter, and the entire process had to take less than 90 minutes or else it had to be repeated. The dilutions were based off an assumption that the lead in the soil was about 50% bioaccessible in order to have a target concentration range between 50 and 150 parts per billion. The solutions were diluted using 1% nitric acid and then analyzed using ICP-MS. This is another page from the DEQ activity book, and it reminds people not to eat food that fell on the ground, so no 5-second rule, and to bring clean water, never using river water, and to make sure you have a clean eating surface. And now some results. These are the results from a LIBS analysis. The images are the locations, and the yellow dots are the individual sites where soil was collected at 0 to 1 inches and 1 to 6 inches. All values on the slide are reported in parts per million. While there were a couple samples that registered below the level of detection in location 1, the vast majority returned at truly terrifying lead levels, with the maximum value of 89,000 parts per million. Here are the bioaccessibility results, also reported in parts per million. While the numbers are lower than the LIBS values, which was to be expected, they're still extremely high for both surface and deeper samples. The same location that was 89,000 parts per million is almost 63 parts per million for bioaccessibility. However, on location 1, where the LIBS results return less than the limit of detection, the bioaccessibility values were above the device's limit of detection. This page of the DEQ activity book reminds people to eat the fillet of the fish, since heavy metals accumulate in the organs. It also lists a website where people can go to stay up to date on fishing advisories. This table summarizes the LIBS results. It is separated out by location and then by soil depth, and provides a range of concentrations at each location for that depth. I would like to draw your attention back to the surface of location 2, which had the highest concentration of 89,000 parts per million. That's equivalent to 8.9% of that soil being lead. The asterisk denotes that 2 of the 6 surface samples at location 1 registered below the limit of detection, and all of the 1 to 6 inch samples reported below the limit of detection. When comparing the uphill and downhill data, it can be said that in general, the uphill concentration was lower than the downhill concentration. This could be because of runoff, especially since most of the surface samples were the more concentrated. To put this in perspective of remediated soils in town, soils above 1,000 parts per million had the top foot of soil removed. The majority of these sample sites were well above that limit. As for the LIBS being a viable field analysis for heavy metal concentration in soils, there would need to be a way to form pressed pellets on site. If that is possible, then it would be extremely useful in the field due to the quick results and the ability to provide immediate heavy metal concentrations. The bioaccessibility results are summarized here with a high of almost 63,000 parts per million and a low of 16.4 parts per million. This means that all samples were above the LIBS limit of detection, even though it reported 8 samples below the limit of detection. Another contradiction to the LIBS results was that there was no general trend for the concentration of uphill versus downhill sites. However, the trend that the deeper samples having a lower concentration of lead than the surface was also seen with these results. Bioaccessibility is supposed to be reported in percent of the total lead in the sample. Using the LIBS results for this, 130% of the lead of the soil is bioaccessible, with the range being from 26% to 268%. Now, obviously this doesn't make a lot of sense, and in general, the EPA's bioaccessibility model assumes that the amount of the bioaccessible lead for children is 30% and for the adult is 12%. Another reason that this number could be so high is that the lead that is present in the soil is incredibly bioaccessible. Some more reasons for why the numbers could be so skewed is that first, the method used to extract the lead from the soil was deviated from because I ground the samples instead of just sifting them through a 150 micron screen. The 150 micron size of particulates was chosen because that's a size that tends to adhere to children's skin. And secondly, the LIBS results are useful for a general idea of the concentration, but not for precise calculations. An ICP-MS analysis would be needed to increase the quality of data here, and that leads to the next step of the research. Processing the collected samples by using microwave digestion and ICP-MS would provide a higher quality of data, which would allow to have better quality of data for the bioaccessibility, as well as a more reliable point of comparison for the 1990s data. This could be expanded upon to include a repeated bioaccessibility assay that conforms to the method better. This too would improve the bioaccessibility data. Moving forward, with research in the Bunker Hill site could include sampling from other sites in the 1990s to understand how the concentrations have changed over time, as well as working with the EPA and DEQ to locate new testing sites that also have a high probability of being developed in the future. Even though this research has highlighted some heavily contaminated sites, there has been significant progress made at the Bunker Hill Superfund site. The average blood lead level has dropped dramatically from almost 70 micrograms per deciliter, with some children having over 100 micrograms per deciliter, and a record of one child having 164 micrograms per deciliter, to now below the CDC health standard of 5 micrograms per deciliter. This has been tracked through a summer blood testing of the students in the area. And as I mentioned earlier in the presentation, over 7,000 properties have had their soil remediated, and there are more properties planned going forward. There is a new water treatment plant being built that can remove up to 1,800 pounds of zinc per day and has a completion date of later this year. Repairing over a century of mining damage is expensive, and most of the mining companies responsible for this have been bankrupt. The only recommendations I can offer going forward would be to follow up on previously soiled sample sites and a more aggressive signage and information release to the public about the high concentration of the lead in the Hillsides area, and perhaps even limiting access to the specific areas that have the highest concentration of lead. Especially with the outdoor activities in this area, people just love to enjoy this beautiful scenery. Having them limit the exposure to highly concentrated lead in the soil would be a very good step. I would like to thank Pacific Lutheran University, especially the chemistry department, for allowing me to research a topic near and dear to me. Dr. Tan, who provided insight and guidance along this journey. Dan McCracken of the Idaho Department of Environmental Quality, who provided information relating to the Bunker Hill site, and he granted me permission to collect samples on state lands. I would also like to thank Victoria, my fellow soil lab researcher, for helping me find a way into streamlining this research process. And then last but not least, I would like to thank my family for all their support, which included going out on a hot August day to collect my samples. If you have any questions or comments, please leave them in the section below, and thank you for your time.